We've examined using the simplex method to solve standard maximization problems. And now we're going to take a look at what is a standard minimization problem and how can we use the simplex method to solve those. At some various points, I'm going to be referring to some earlier videos, and I'm going to try to remember to link those. So a standard minimization problem, obviously the objective function is to be minimized, but also your variables are non-negative. And if you put your other constraints besides the non-negativity constraints into standard form, then you would have them greater than or equal to a constant, which I can't remember for sure, but perhaps that constant needs to be non-negative as well. This is a minimization problem that we looked at via the method of corners. And I had said in that video that I wanted you to compare it to a standard maximization problem. Here's the solution we came up with. 20/7 comes 25/7 for A and B. That produced the minimum value of the objective function C, 2100. And here was the standard maximization problem that I wanted you to compare to. I said that we were seeing a lot of the same coefficients, but in different places. If we take the original first problem as the standard minimization problem, I'm taking the 1, 2, and 10 from the first regular constraint as the first row, the 4, 1, and 15 from the second regular constraint as the third, and then the 360, 300, and it doesn't matter what I put for the third thing. This is not a simplex tableau. It's just a tableau of coefficients that we're seeing in the original first problem, which is our standard minimization problem. What I'm showing here is what we saw happen to the numbers when I said to compare it to the standard maximization problem. Now we would see 10 and 15 in an objective function that were to maximize, and then regular constraints besides non-negativity of something times 1 plus something else times 4 less than or equal to 360, and similarly for a second regular constraint. If we go back, you can see that here. So what's going on from here to here? Color-coded it as one way of looking at it. There's other ways that this could be explained, but I'm saying in this demonstration that row 1 is becoming column 1, row 2 is becoming column 2, and row 3 is becoming column 3. This is transposing a matrix. Not only could I have said that a particular row becomes a particular column with the same number, vice versa, I could have said that each column 3, for example, is becoming row 3. Or we could say that at the most fine grainy level here, that's A sub I comma J, that's in matrix A, row I, column J. In a transpose that you get a new matrix where the row and column numbers are switched. If you have an entry in row I, column J, you're going to see that same number in the transpose at row J, column I. So let's call this a dual problem. The original primal problem, that first problem, of a standard minimization problem. This is the dual problem, which is a standard maximization problem. And we've also seen this before. Not only did we solve it by the method of corners and get that 120, 60 for x1 and x2, produce the maximum value of z of 2100. We solved that by the method of corners. But now if I put in the original variables from our standard minimization problem of a and b, make those the slack variables in the dual problem. We had already solved this problem, although I probably named the slack variables differently previously. We solved this not only by the method of corners, as I just reminded you, but we've also seen this by the simplex method. This is what we started with. And then that's the initial simplex tableau. This is what we ended up with. And we can see that our unit column here under x1, we've got the 1 in row 2, and we trace over to the far right. That's giving us the x1 is 120. x2 has a unit column, so the 1 is in the first row. Trace over to the far right, and we have the x2 is 60. And at the bottom, we see the 2100. We know this is optimal because there are no more negatives in the objective row. But do you notice anything else? If you look straight down under A and straight down under B, we're seeing the coordinates of what we found to the solution to the primal problem, that first standard minimization problem. And the minimum value of C is the same as the maximum value of Z. So you can turn a dual problem, you can turn a standard minimization problem, a primal problem, into a dual problem of a standard maximization problem. And be very careful. Once you've solved use the simplex method to solve the standard maximization problem, the dual problem, the table, when read a different way, is giving you the solution to the original primal problem. I'll show another standard minimization problem being solved by turning it into a dual problem, that is a standard maximization problem, and applying the simplex method in another video that'll be uploaded, say within the next day or two. That's all for now. Hope it helps. Stay safe and healthy.